or how weak the disorder is, you flow to the Anderson insulator. Okay, and so this system is a little bit different, and I think in the next view graph I might be able to give you an argument that will convince you that this can't be localized. So I'll see if I can do that. So this poses the question. So there's something very special about this quantum spin Hall insulator that we sort of stumbled on thinking about graphene. Okay, and so what is it about the bulk that tells it that it has to have these special edge states which are protected by time reversal symmetry? And so there must be some topological structure. And so in fact there are two and only two topological classes of time reversal invariant insulators. And just so I have an idea, so I'm going till 11, is it? Okay, good. Okay, so let me convince you that there are two and only two classes. Okay, and again, the way I'm going to do this is by thinking about the boundary, about the edge of this two-dimensional system. Okay, and so again, I have a two-dimensional Hamiltonian with time reversal symmetry, which imposes this constraint. And so I want to argue that there's a Z2 topological invariant that distinguishes two different kinds. And so if I think about the edge states, so let me go back to thinking about these edge states, and so in general, so what I'm going to do is I'm going to plot the energy bands as a function of momentum along, say, a strip. Okay, so and I'm only plotting half going from k equals 0 to k equals pi. The other half going from k equals 0 to minus pi is, because of time reversal symmetry, is just a mirror image of this. Okay? So now, so at k equals 0, I have the valence band and the conduction band, and it's always possible, you know, depending on what the details of the potential at the boundary is, that there could be states which are inside the energy gap but are localized at the edge. Okay, so that's always possible. But the thing that we know is that if we have time reversal symmetry, then they have to be Kramer's degenerate. Okay, there have to be two states. Now, if I move away from k equals 0 and I have a spin-orbit interaction, then in general this Kramer's degeneracy will be split because, again, this guy's partner is at minus k. Okay, so these states have to be Kramer's degenerate. Now, at k equals pi, again, since pi and minus pi are the same momentum, these also have to be Kramer's degenerate. Okay, so now you can understand why it is that there are two and only two classes. It's because there are two and only two ways that the Kramer's pair here can connect with the Kramer's pair here. Okay, either they can connect pairwise like this, and if they connect like this, then you know the way I've drawn it here, I have some edge states. Okay, there are states at the Fermi energy on the edge, but those edge states don't have to be there. They might be there, but they don't have to, because I can imagine pulling these down smoothly and just getting rid of them completely. Okay? So you might have edge states, but you might not. Another way you can say it is that the number of intersections of the Fermi energy of the bands in between k equals 0 and pi has to be even. Okay? So it could be any even number. That even number might be 0, so you don't have to have the states. Now, the other way you can do it is they could connect, they could sort of switch partners. The Kramer's pairs could switch partners going from 0 to pi, and if they do that, then there's no way you can get rid of them. Okay, you can move these up and down all you want. There always has to be an odd number of crossings in between 0 and pi. Okay, and so these ones you can see that you can't get rid of. Okay, so now let me try to answer the question about Anderson localization. And so I'm going to play the same game that I played with Laughlin's argument in the quantum Hall effect. What I'm going to imagine is that I have a big system, okay, which is disordered, but I'm going to put it on periodic boundary conditions. Okay? And then what I want to do is I'm going to consider my entire system to be one single unit cell. Okay? And So then it has a band structure, okay, and so then I can have a magnetic flux that changes the boundary condition for how the wave functions here match up with the wave functions on the other side. Okay, so I can twist the boundary conditions, and that is like changing the value of K in this single unit cell. Okay, now if it is a topological insulator, then the spectrum of the edge has, now there are going to be lots and lots of states because it's very long, but if I follow them, then the Kramer's partners, since it's finite, then the spectrum at the edge is going to be discrete, and it's going to have Kramer's partners which switch partners as a function of K. Okay? Now, if you were Anderson localized, then your states would be exponentially localized, and there's no way they could know what the boundary condition is. Okay? So by definition, localized states are insensitive to the boundary condition. So if you had localized states, there's no way they could have this zigzag partner. Okay? And so that guarantees that every state here is extended and goes all the way around, and every state knows about the twisted periodic boundary conditions that you put on. Okay, and so that guarantees that that these states cannot be Anderson localized. Yes.
So if they switch partners, that sort of guarantees that you need two edges, sort of a strip. What I'm imagining.
Well, you do need two edges, but why are you saying that that you need two edges of this? I mean, this picture here is all characterizing just a single edge. There's going to be another set of these pictures which are localized on the other edge.
Right, that's what I'm asking about. Is system with just one edge physical?
No. So I can't, with time reversal symmetry, I cannot have this picture in a purely one-dimensional system. Yeah, it's just like I can't have a single chiral edge state. Okay, so I cannot have the helical edge state in a purely one-dimensional system. Yeah.
Going back one slide, just to look at a simpler picture. Can you go back one slide?
Sure.
So at this direct point, if I define projection operators, let's say for the green line, so that I project onto that eigenstate, and I vary as I go along the green line, and I come back because I have this rho 1 torus.
You mean I'm going all the way around?
I'm gonna end up on the red line, right?
Ah, no. You see, that's the reason. That's the origin of the doubling theorem. You see, what has to happen is as you go along, you have to intersect the bulk states. You see, this state is not coming and matching up onto this one. So in fact, what will happen, so if I do it in a finite strip, what you will find, in fact, is that if you follow this discrete state around, what will happen is it will come back on the other, it will mix with these states which are extended across the entire width of the strip, and then this state will come out on the other edge. Okay? And that's the same thing that happens, maybe it's more obvious that that's what happens if you have let's say I don't have the, yeah, say if I have this picture, okay, so this picture is on one edge, okay, so you could ask, well, what happens to this if I follow it up? Well, what happens is it comes out, on the other edge there's a line that's coming down like this, okay, so that's what happens to it. Okay, good.
Sorry, just quick, if you have translation symmetry breaking disorder,
Yes.
then how do I visualize that K-space plot? In principle, that whole thing.
Well, no, that's the reason why I gave this argument, which was I want to think of the entire system, which is disordered now, as being my unit cell. So then the momentum, the K that I'm using here, is really the phase twist of my boundary condition. Okay, and so that I'm allowed to do even when I don't have, so in a sense I have a translation symmetry, which is that, I have the periodic boundary condition, so I can, it's like I'm making, you can think of it, I'm taking my system and I'm making many copies of it, periodically extended, and then thinking of that as a band structure, right, with K. That, you could think of that's what I'm doing. But I don't think I'm relying on the translation symmetry of the lattice translation symmetry in order to do this. Okay. All right. Let's see. Where are we? Okay. So let me try to. So we have. There's this. So this tells us that there should be some. Topological invariant that has two values, 0 and 1, okay, which tells us whether the edge looks like this or whether it looks like this, okay? And so in the Laughlin, in the quantum Hall effect, we had this very nice physical picture of what the Chern number meant, okay? In terms of the Laughlin argument, if we thread a flux, then it tells us how much charge is pumped. Okay? And so let me try to give you a similar understanding of the Z2 invariant in that case. Okay? Because the sort of mathematical description of the Z2 topological invariant is a little bit harder than the Chern number. Okay? And so let me try to give you some physical picture. So let me remind you that if we do the integer quantum Hall effect, we thread a flux down the cylinder, and then we pump an integer number of electrons, and that's the Chern number. Okay? So now let's imagine that I wrap this quantum spin Hall effect on the cylinder. And I can think of it that, it's like I have two copies of the quantum Hall effect, +1 for the upspins and -1 for the downspins. Okay? And I want to think about a similar sort of flux threading Gedanken experiment. And but now what I want to do, obviously if I thread a flux, then a whole flux quantum, then the Chern number is equal to 0, so I come back, no charge is pumped. Okay, but what I want to do is I want to think about what happens when the flux that I thread is 1/2 of a flux quantum. So I thread a flux h over 2e. Okay? Now, the thing that is special about h over 2e is that, you can always gauge away an integer number of flux quanta, right? So 0 is the same as h over e, which says that h over 2e is the same as minus h over 2e. Okay? And so what that means is that when you have the flux of h over 2e, you basically have time reversal symmetry. Okay? So there are 2 points where you have time reversal symmetry. You have time reversal symmetry at 0 flux, and you have time reversal symmetry at flux h over 2e. It's sort of like, in the Brillouin zone, you have time reversal symmetry at k equals 0 and at k equals pi. Okay? It's the same sort of thing. Okay? So let's think about what happens if I thread a flux of h over 2e. Now, of course, I break time reversal symmetry in between, but at the beginning and at the end, I have time reversal symmetry, which means I have Kramer's theorem. Okay? And now I want to think of Kramer's theorem. So what happens is that when I thread half a flux quantum, then what I'm going to do is I'm going to transfer half of an upspin to the right, and I'm going to transfer half of a downspin to the left. Okay? So at the end of the day, I have changed the local spin at the end by a spin a half. Okay? And so what this means is I have gone from locally having a ground state where all of the states are paired, so there's no Kramer's degeneracy in my ground state, to a state where I have a single unpaired spin a half. So I have a Kramer's degeneracy. So now I'm talking about the sort of many-body states. I go from locally having no Kramer's degeneracy to locally having a Kramer's degeneracy. Okay, and so this is, so if I had a trivial insulator, then it would have to be insensitive to the magnetic flux, and so this couldn't happen. Okay, and so this is what happens if I have a topological insulator. Okay, all right. Do I want to do this? Does anybody want to know what the formula for the Z2 invariant is? We can skip this and talk about, I think maybe I will, this is a little bit technical, so I think maybe I will skip this and go to, so you can calculate this Z2 invariant. Given a band structure, you can calculate it, okay? And it's not that easy to do, and there are different ways you can do it. Some of them are more easy to implement on a computer than others. This one is not so easy to implement on a computer. So what it is easier to do is to figure out the Z2 invariant when you have some extra symmetry. Okay, so for instance, if you have the conservation of SZ, like I did in the model, which was just 2 copies of the Haldane model, the Hamiltonian only involved SZ, so SZ commuted with the Hamiltonian, which means I really could think of it as 2 independent quantum Hall states for the up and down spin. Then the up and down spins each have their own Chern number, okay, which of course time reversal symmetry says they have to be opposite to each other, but the Z2 invariant is just the parity of those Chern numbers, whether they're even or odd. Okay, and so this of course survives even then if I turn on a perturbation which violates the conservation of spin. So there's another symmetry which actually turned out to be quite useful that one can think about, which is to think about a system that has inversion symmetry. And then it turns out that one can figure out the Z2 invariant just by thinking about the parity of all of the occupied block states at the different parity invariant points. So in a 2-dimensional band structure, there are 4 of these points where k and minus k are the same point. Okay, I can have 0, 0. Pi, pi, 0, pi, and pi, 0. Okay? And at all of those points, the eigenstates, if you have inversion symmetry, are going to be parity eigenstates. So they're either even or odd under parity. Okay? And so if you take all of those eigenvalues at all of the parity invariant points and you multiply them together, then you get something which is either plus or minus 1. And if it's minus 1, then it's guaranteed that you have a topological insulator, if you have an insulator. Okay? So this actually is a sort of, if you have inversion symmetry, this is a quick way of determining whether you have a topological insulator or not. And actually, historically, that's the way we sort of figure out the first example of a topological insulator, which was this alloy of bismuth and antimony that Zahid told you about yesterday. Okay. Let's see. What to do? I think what I'm going to do is I'm going to skip. I think Amir Yacobi is probably going to talk about the mercury telluride experiments, which were the sort of first experiments that demonstrated the 2-dimensional quantum spin Hall effect. So I think I'm going to skip through this, and so I want to get to the 3-dimensional topological insulator. So what we introduced was so now we understand that in 2 dimensions there are 2 classes of insulators. Okay, so there's the topological insulator and the trivial insulator, and so the natural question that you can ask is, what about 3-dimensional crystals? Could there be topological classes of those? Okay, and so in fact the answer is yes. And again, the sort of a simple way that you can think about it is to think about what happens at the boundary. Okay, so now the boundary of a 3-dimensional system is a 2-dimensional plane, and so I can ask myself, what sort of kind of surface states could I have now as a function of momentum in this two-dimensional Brillouin cell. Okay, so again, the story is the same as in the edge state case.